All right. Uh, Section 5.3. We're going to be looking at specifically how to graph. My personal favorite. I really enjoy it. I know I make jokes if you've been in my previous classes about hating graphing, but it's actually one of the things that I think is truly one of the most creative and most useful skills in algebra because it's the ability to take something that is an equation and turn it into something that people can understand. Like if I gave the average person hard data, it's very difficult to comprehend. Like if I said the trend of, people entering the country is this graph, or this equation, they'd be like, what does that mean? I don't get it. But if I give them a graph, they can see it and see and understand what it's going to mean. That's a really useful skill. Seeing a picture of these functions and understanding how to get from the equation to the picture to make sure it actually makes sense, it's a unique skill. And it's one that sadly is not emphasized very well in previous math classes. You are taught to graph linear functions, you're taught to graph quadratic functions, and even we did that in the previous two sections. But one of the more creative and abstract uses of algebra is to graph polynomials and to see how a polynomial can be graphed using basic information like we're going to talk about today. Now, as we talk about today, there will be numerous different approaches that could work for a single problem. In a problem, you may be asked to factor. You may be asked to use the fundamental theorem of algebra. You may be asked to determine something called multiplicity, which we'll talk about later. All these things are very similar and have very similar aspects that go into the graph, but they are unique. Some are easier, some are harder, and it really, truly depends on how you approach the math and how you understand its approach to the graph. So let's start by talking about the easiest subject, the y-intercept. We've mentioned before, and I'm going to do this problems today in two parts. I'm going to have on one page all the work we're going to do, and on the other page just straight notes. So the y-intercept. One of the things to know about the y-intercept is the definition. This is where we're going to cross the y-axis. So if we think about a picture of any given function, like so, the y-intercept is right here. Remember, this is the y-axis, this is the x-axis, and so this is the y-intercept. We talked in the last chapter about how the y-intercept often is referred to as things like the initial value. It's usually, in a real-world sense, the starting place, because typically we start talking about 0. Negatives are only taken into account when we need to. And so the y-intercept is by far the easiest to understand. It's where we cross the y-axis, and it's the easiest to find, because it is when x equals 0. If you look at the graph, that makes sense. Because remember, the x-axis is the one that's going left to right, and here is where x is 0. So on the graph, this dot will always have the point 0, comma, b for the y-axis. It's just how the y-intercept works. And so to find it, you can take 0 and plug it in for your variable. This will always tell you where the y-intercept is. This is the easy of the two. The more complicated of the two is the x-intercept. The reason it's more complicated is twofold. One, when it comes to y-intercept, notice that there's only one of them. Compared to in this graph, there are actually three, there are actually three x-intercepts. So x-intercept, x-intercept, and x-intercept. So, frankly, usually for x-intercepts, there's often more of them. But not always. It is possible to have a polynomial that has 0 x-intercepts, although it is less possible to have one that has 0 y-intercepts. So, when it comes to x-intercepts, there's often more of them, which means there's often more work to do. Because there's more of them, these can involve a few different concepts. So first of all, these can be turning points, which we talked about in the last section. They could be just straight intercepts. These could also be something that we're going to refer to as multiplicity. And so depending on the problem and the context, your x-intercept can fill multiple roles. It could be a place where it also turns. It could be a place where it's an intercept only. It could be a place that has multiplicity. And so in a given problem, there's more information contained in just x-intercepts. However, there's one thing that's big to note about an x-intercept. It is when the y value equals 0. Which means that to find it, you need to take f of x and set it equal to 0. This is the most common step to use to determine the intercepts, is setting something equal to 0. Either you set x equal to 0, that's how you find the y, or you set y equal to 0, and that's how you find the x. However, because we're dealing with polynomials, this function may not always be nice. And so let's take a look at our first couple of examples to kind of showcase where we can have different methods to get an x-intercept. The first example I want to talk about, and before we go on, your homework tonight, 7 through 63, every other odd. Nice little assignment. Let's start by looking at some evens, including specifically number 6. So I have my homework up here. It says we have c of t equals 2, t minus 4, t plus 1, and t minus 6. Okay. So when it comes to these equations, there's a simple way to determine where the x-intercepts are going to be, or in this case, we'll follow the t-intercepts. Notice that we can use x and t interchangeably because in the problem, t is the main variable, just like x is normally the main variable. So one of the best ways to approach these problems, if you're trying to find the x-intercept, is to have it be in factored form. If your function is in factored form, then you can use something called the fundamental theorem of algebra to find the solution. Let's take a look at number 6 and talk about how that works. We're going to now use the fundamental theorem of algebra to find all the intercepts in this problem. The fundamental theorem of algebra states that we're going to take this function and set it equal to 0. Because remember, that's what we need to do in order to find any and all x, or in this case, t intercepts. One of our options is we need to take the function and make it equal to 0, which we just did. But now how we actually get to the solution is using the fundamental theorem of algebra. The fundamental theorem of algebra states that each component that is factored can also be set equal to 0. So 0 equals t minus 4, 0 equals t plus 1, and 0 equals t minus 6. You might notice that I dropped one of them. We did it for these 3, but what about this one in front? Well, in this specific example, the 2 doesn't do anything, because if I do 2 equals 0, that's not really very helpful, because 2 never equals 0. This is the fundamental theorem of algebra. It states that if we have one equation that is equal to 0, we can split it into multiple equations as long as they are factored. So this allows me to use algebra by adding 4 to both sides, by subtracting 1 from both sides, and by adding 6 to both sides, to find the 3 intercepts of this problem, which would be 4, -1, and 6. This is the primary and easiest way to determine when you have your x-intercepts. So by and far, when possible, you want to use the factored form and the fundamental theorem of algebra. And in this case, here's how we did it. We took the factored form, we made sure it was equal to 0. That's just the property of finding the intercept. And then, because it is equal to 0, we take all the pieces, all 4 of them in this case, and set each one equal to 0. The first piece didn't do anything, because 2 never equals 0. But the second, third, and fourth all can be solved now, since they're in separate form, and give us 3 solutions. 4 from this first equation, -1 from the second equation, and 6 from this third equation. So our x, or in this case t-intercepts, are -4, -1, and +6. This is by and far the easiest way to do the problem. Let's compare this now to number 8. On number 8, we have a slightly different equation. C of t is equal to 4t, 40, times t minus 2 squared times t plus 1. If the question asks us to determine the intercepts, as this problem does, then we can apply the fundamental theorem of algebra, which states that we have 0 equal to 4t times t minus 2 squared times t plus 1. And using that theorem, we can take this from one equation into 1, 2, 3 equations. So we'd end up having 0 equals 4t, 0 equals t minus 2 squared, and 0 equals t plus 1. From here we can solve, divide by 4, take a square root, and then add 2, or subtract 1, to give us our solutions of, we have t-intercepts at the following 3 locations, at 0, 2, and -1. So in these factored forms, which you'll notice the first couple of problems are all in factored form, this is by and far the easiest way to approach the problem. So, when possible, if the question asks about x-intercepts, you should always be looking to figure out if it's in factored form, just use the fundamental theorem of algebra. These are by and far the easiest. Now, from this point on, the process gets progressively harder, because as you might notice, not every problem is going to be in factored form. Some forms are just not appropriate to use in this method. So let's take a look at our next problem, which our next problem is actually going to be number 10. And so you may want to put in factored form. If it's not currently in factored form, you may wish to put it in factored form, because again, factored form is the easiest. And so if you can find a way to put it in factored form, it's the best thing you can do. To do so, there are 3 different techniques we have discussed in this class so far. Each one works slightly differently. So, number 1, you can, in fact, factor completely. In this case, I'm using this phrase to refer to factor something from the entire function. 2, I could do what's referred to as standard factoring, or the AC method as it's sometimes called. And then finally, I could do factor by grouping. Now, each one of these has its own pros and cons. This works if you can take something from everything. So if you have 3 different pieces, you can factor something from all 3 of them. Not just the first 2, not just the last 2, not just the middle ones. Like, you have to be able to factor it from all, if all pieces contain something. Maybe they all contain an x. Maybe they all contain a 3. Or maybe they contain variations that can get you an x or a 3, but they have to be in all pieces. Okay? The standard technique works best if it's a quadratic. So quadratics, remember, are anything with a power of 2 as its main power, as its degree, as we called it last time. Factor by grouping, this one's typically used in more general settings. There is a 4th technique you can use. These are referred to as special cases. These are ones we normally have listed on the board. And so let's remind ourselves. We have difference of squares. This is one of the most common ones, where you have a squared minus b squared, and you can factor it into an entirely new equation. A plus b, a minus b. It's just a shortcut way to get the solution faster. You can also have sum of cubes and difference of cubes for much the same reason. If you're doing things like sum of cubes, that'd be a cubed plus b cubed, and difference of cubes, a cubed minus b cubed. So for sum of cubes, it is written as a plus b times a squared minus a b plus b squared. And difference of cubes is written very similarly, just with the plus and minus the first two switched. A squared plus ab plus b squared. In any given problem, any of these four could be applied. It depends upon the problem. I will tell you from experience, the most common one is number 2. The next most commons are 1 and 3. They're very common, but not nearly as common as just number 2 is. And then finally, the special cases is rather rare, but when it does pop up, it is actually one of the best ones, because they're relatively easy to factor, because you just have to memorize a formula. Let's take a look now at number 10. Okay, number 10 states we have C of t is equal to 2t to the 4th minus 8t cubed plus 6t squared. Now, if we look at our list and see what our options are, okay, we could try to see if anything comes out of all the pieces, so factoring completely. We could look to see if it was a quadratic, but sadly it's not a quadratic. We could try to factor by group. Factor by group, again, is less typical, okay, but it's a good fallback if you're finding that the first two are not working. And then we should always check to see if it's a special case. Looking at this problem, I can clearly see it's not one of the special cases. It's just not. It's not a squared minus b squared, because we got these fourth powers. It's not a cubed and b cubed, because again we got these fourth powers and these second powers. So it looks like I need to either do the first one, factor completely by taking something out of everything, or the third one, factor by grouping. So it turns out for this one, the best step is to factor something out of everything. So in this case, what can come out of each term? Well, two things actually. A 2 can come out of every term. I have 2, I have 8, I have 6. I can take a 2 out of 2, I can take a 2 out of 8, I can take a 2 out of 6. There's also one more thing that comes out of everything, and that is a t squared. In this first term, there are 4 t's. In this one, there are 3 t's. In this one, there are 2 t's. And if I take a 2 out of each of them, I can tell what's going to be left behind. There will be 2 t's left in the first one. So if I take a 2 out of there, it would become a minus 4. But there'll be 1 t left because I took 2 of those t's away. And then plus 3. So already this is much closer, right? This is now in factored form. We could consider doing our steps. But the thing about it being factored in form is you want to make sure you factor as far as you can, because it's not technically in factored form until it's fully factored. Okay? This right now is partially factored, but it actually factors once again. In this case, 2t squared doesn't factor any farther, but this term does. And some of you might remember this. If not, this would be a good time to remind yourselves. We have negative 4 on bottom. We have a 1 and a 3, making it 3. The factors of negative 4 that are from 1, 3 would be negative 1 and negative 3. So this would mean we have t minus 1 times t minus 3. You can, when it comes to a quadratic, this is one of the best techniques to use, is to factor it by the standard technique. In this case, it's the X method, as discussed in class. So this is now in fully factored form, which means we could use our factored steps using the fundamental theorem of algebra, just like number 6 and number 8. But notice we didn't start in factored form like number 6 and number 8. We had to put it in factored form, which is a big step to take. With number 10, now that we're here, we'll actually be able to take the next step pretty well. We can split this from one problem into 3. We have 2t squared equals 0. We'll have t minus 1 equals 0. And we'll have t minus 3 equals 0. From here we can find our solutions, dividing both sides by 2, and then taking a square root, adding 1 to both sides, adding 3 to both sides. We have 3 solutions. So if the question asks us what are the x, or in this case t-intercepts, the t-intercepts are 0, 1, and 3. This is one of the best techniques we have. If it's not in factored form, we can put it in factored form. Now, this takes practice, which is why we have some practice problems today. And we'll be looking at number 12 next to get some more practice on it, and so we can see at least one more example of how we can factor these. And we'll actually do a couple of them, because I think it's super important to get through and practice some of this factoring stuff. Because if you're not comfortable factoring this expression, then these problems become very, very, very difficult to do. So let's look at number 12 now. In this problem, just to reiterate some points here, we had to factor something out of everything. We had to do a standard AC method to put it in factored form so we could use the fundamental theorem of algebra. We had to do 3 completely different steps to solve this problem. And the thing is, in any given problem, those 3 steps could all happen. Or we could add in another one. We could have to do factor by grouping and then do one of these other ones. We could have to factor completely out of everything and then factor by group and then do the factored form. There's so many different ways you can do these problems. You have to be paying attention to how they all fit together. You can usually see some patterns if you're willing to try them out, but in general, you have to be willing to try out each one of these steps in a given problem and say, is there something I can factor to everything? Is it a quadratic? Maybe I should group things together and see how they solve. And so for each problem, it is important to go through those basic steps and see how they're done. Let's look at number 12 now. Number 12 and number 10 are very similar, so let's take a look. Number 12 states we have f of x equal to x to the 4th minus x squared. Okay, I look at the problem, I instantly notice it's not in factored form. That's an issue. So, first step, I'm going to put it in factored form. How do I do that? Well, I go into my list. Let's see. I could try to factor something out of everything. I could try the standard method. I could try factoring by grouping. I could try to look for special cases. In this case, I always start with number 1 because it's a really good one to start with if you're not sure. So I'm going to see if there's anything I can take out of everything. And no offense, but it will almost always give something better to work with than what you started with. In this example, there is one thing we can take out of everything, an x squared. If I take an x squared out of everything, this first term goes from x to the 4th to x squared, because I took 2 of the x's away. The second term, I take both x's away, which means I just have a negative 1. Now, I have partially factored, but I notice this one is not fully factored form. It's x squared minus 1. Now, I go back to my list. I've done the first one. Check. Now, I could go to the AC method and start going from there. But in fact, I'm actually going to go to this bottom one because I see it's a special case, a squared minus b squared. In this case, in my problem, I have x squared minus 1. So really this is x squared minus 1 squared. And so I can actually do a rewrite. This becomes x squared times, so according to our difference of squares formula, this will become the first plus the second, so x plus 1 times the first minus the second, so x minus 1. I can get the same solution if I was willing to do the AC method, but this one is faster. And so if I know my pieces, if I know my forms, this will always be the faster way. Now that it is in fully factored form, and I know it's fully factored because I have x squared by itself, that's factors that can go. I have x plus 1, that's a linear term. I have x minus 1, that's a linear term. So when I get back to here, I can actually solve. I can use, as we discussed before, the fundamental theorem of algebra, set this equal to 0, and then do it in 3 pieces. My x squared equals 0, my x plus 1 equals 0, and of course my x minus 1 equals 0. And then I solve each piece. Square root both sides, I get x equals 0. Subtract 1 from both sides, I get x equals negative 1. Add 1 to both sides, I get x equals positive 1. Which means that my x-intercepts for the problem are 0, negative 1, and positive 1. Notice that for this problem, I had to use multiple techniques to get to the solution. This is common. It's not just going to be one type of problem every single time. You have to be willing to look at a problem and ask yourself which step is the best. This is what separates Algebra 2 from college algebra in many ways, is that in a given problem, you can use multiple techniques to solve the problem. You're not just expected to be able to apply one to any problem. So, we started here. We factored x squared out of both terms. Excuse me. We then used a property called difference of squares to split this piece apart. And then we used the fundamental theorem of algebra to do all 3 pieces separately, getting our 3 unique solutions. Let's do one more. For this one, let's do number 16. And let's talk about how we can actually solve this problem using our last remaining technique that we haven't touched on yet, which is going to be factor by grouping. So, 16 has the following equation: x cubed plus 2x squared minus 9x minus 18. Okay, and this function says f of x is equal to that. Cool. So, I look at this problem and I notice it's not 3-termed, so I can't factor anything out of everything. Like this one has x's, 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 but the last one has no x's, so I can't take an x out of everything. This one both has 9 and 9, but these two don't have 9s in them, so I can't take a 9 out of everything. This one has 2, and this one has a 2, but this one doesn't. And so it seems like there's no term that will come out of everything. So in this case, let's look at factor by grouping. If you look at factor by grouping, what factor by grouping states is take the first 2 terms and just try to factor those. Take the second 2 terms and just try to factor those. Rather than looking at the entire function, we look at small groups of the function. When I do it this way, watch what happens. This first one, I can take an x squared out of everything, leaving me with x in the first term and 2 in the second term. The second one, I can take a negative out of both pieces and a 9 out of both pieces, leaving with an x and a 2. It's common to mistake some signs in here, so always be sure if there's a negative in both pieces, you can take a negative out, leaving a positive behind. This is a key indication that factor by grouping was the right choice, is if these two match. Because if they match, we can actually factor both of them, meaning we end up with x squared minus 9, which you notice is this first piece, and the second piece, put into one parentheses, and x plus 2. This is factor by grouping. Notice we took this original function and rewrote it as 2 factored terms. Just like before, we're not yet finished. And just like before, we're actually going to use the exact same trick to get out of it. The second term is fully factored. X plus 2 is great. But this first term, x squared minus 9, you'll notice is just x squared minus 3 squared, which means I can now use difference of squares. So this would become x minus 3, x plus 3, and x plus 2, using difference of squares. So this got me from the original equation down to this factored form. And now I can use the fundamental theorem of algebra, set it equal to 0, and do my three parts. X minus 3 equals 0, x plus 3 equals 0, and x plus 2 equals 0. Which leaves me with three answers. X equals 3, x equals negative 3, and x equals negative 2. Or, as the problem specifically states, my x-intercepts are 3, negative 3, and negative 2. So, these are the four different techniques we primarily use. You have factoring one term out of all the pieces. You can use the standard AC methods from quadratics. You can factor by group, which is typically a more general rule, but there are very specific cases where it works very well. And there are very specific cases, like the difference of squares, sum of cubes, and difference of cubes. Notice that these last two are rarely used. This first one, fairly common. It just depends upon your experience with the problems. And it's very common to see difference of squares in conjunction with factor by grouping, because factor by grouping often leads to the same situation we had here, where we end up with x squared minus 9 as one of our terms that can then be split. It just happens to be really common that these two go together. So that's our first piece of the homework, you'll notice. Let's take a look at the next piece. The next piece deals more specifically with something referred to as the intermediate value theorem. So let's pull this up. So if questions ask anything about y-intercepts or x-intercepts, we now have ways we can do them. We can do them from the picture, or we can do them from the equation. We can do them from the picture, or we can do them from the equation. Notice which one is preferred. That's why graphing is considered to be such a good skill in math. Is because if you can do the picture, then finding the x-intercept is a factor of, can I look at the picture and can I see this dot? It's so much easier if you can graph it. Now, let's now look at something called the intermediate value theorem, or IVT, as it is typically called. The intermediate value theorem I'm actually going to pull up the book's definition here. I think the book's definition is very nice, even if it's not the easiest to explain. So let's go to the book. Let's go up to the IVT. There's some great examples in the text to help out with this, if you want to take a look at them. Here it is. The intermediate value theorem. Let f be a polynomial function. So all the problems we've talked about today are polynomial functions. So this applies to every one of them. The intermediate value theorem states that if f of a and f of b have opposite signs, then there exists at least one value c between a and b such that f of c equals 0. Let's explain this more thoroughly. So it states, you have to have a polynomial function for this to work. That's the first thing. If you have a polynomial function, it has to be assumed that it's polynomial. You have to have f of a and f of b, which, if you remember back, f of a is going to be a y value. F of b is going to be a different y value. And they have to have different signs. What does this mean? Well, f of a can be positive, but that means f of b has to be negative, or vice versa. F of a can be negative, but f of b would then have to be positive. They have to have different signs for this to work. So one of them has to be positive, and one of them has to be negative for this to work. If f of a and f of b have different signs, then there exists a c. Now this C must be somewhere in between A and B. Where? Notice the function doesn't say where. It could be in the middle. It could be close to A. It could be close to B. It doesn't say. And it states that C has to exist such that f of C equals 0. I'd like you to note this little picture up here. And I'm going to zoom in a little bit to make it a little easier to see. Boom. Notice that if I pick my A to be 2, then my f of A, the y value of 2, is negative 3. It's a negative number. If I pick my B to be 3, the value for 3 is actually up here. It looks like it's at about 2, or pretty close to it. Again, let me zoom in a little farther. There we go. Notice that at 2, my f of A is negative. At 3, notice this little gap here. That's really important. At 3, my value is positive. What this means is there's a dot right here that is between the 2 and the 3 where the value is a 0. Now looking at it, you could probably take a guess. You could say, it looks like it's about 2.9 or 2.8 and a half. Like you could make a guess and visually be like, oh yeah, of course, there's a number right there where it's 0. But what the intermediate value theorem does is, what if we don't have this picture? If you don't have this picture, it's much harder to see that, there's a dot there. That's, remember, we talked before, graphs are so important because you can have those aha, duh moments. Well, if you don't have the graph, you can still tell me there's an answer there. But to do so, the f of A and the f of B have to have different signs. Now, the primary application of this is if you don't have a graph. So I'd like to now pull up our homework problems that deal with the intermediate value theorem to showcase how this is specifically used. Okay, let's look at number 24. So, number 24. What's 24 state? The following exercises use the intermediate value theorem to confirm that the given polynomial has at least one 0 within the given interval. So in 24, we have the function f of x is equal to x cubed minus 9x. And what we're looking is x equals negative 4 and x equals negative 2. Okay, so the question is, how do we use this thing? How do we show this to work? Well, it's actually pretty simple. To use the IVT, what you need to do is you have to have your A and B already picked out. You then are going to plug in A and B. Once you've plugged in A and B, your third step is to evaluate. Is one of them positive and the other one negative? If that's the case, then the answer is yes. If it is not the case, let's say they're both positive or they're both negative, then the answer is no. So let's look at 24. We have this function. We have the function x cubed minus 9x. We have two values, negative 4 and negative 2. What this tells me is my a is going to be negative 4, my b is going to be negative 2. And you might ask, well, couldn't I switch these around? Yeah, you could, but I'm just being simple here. So we've got our a and our b, so that's step 1. Step 2, we need to plug those in. Everywhere there is an x, we need to replace with negative 4. So negative 4 cubed minus 9 times negative 4. And then get an answer. And then we do negative 2 cubed minus 9 times negative 2. So this top one, negative 4 cubed is negative 64. 4 times 9 is 36. Negative and negative would make that positive, though. So that would be 36. And negative 64 and positive 36 together would make negative 28. So notice how this number is a negative number. If the other answer ends up being positive, then we know there is an answer between the two. So let's try it. Negative 2 cubed is negative 8. Negative 9 times negative 2. Negative to the negative is going to make it positive. 2 times 9 is 18. We need to get positive 10. Notice how we have a negative 28 and a positive 10. We have switched signs. We switched from negative 28 to positive 10. We have f of a being negative. We have f of b being positive. What does it say? Then there exists c such that f of c equals 0. This is actually your answer. Well, and the fact that c is between negative 4 and negative 2. That's the other piece. These two are actually your work. We've got f of a, we've got f of b. That's my work. My answer is this piece. There has to be a c between the two where f of c equals 0. That doesn't feel good if you're like most algebra students, because we're used to getting an answer. We're used to being like, c equals 5. Whatever. We're used to getting a number. And in this case, we don't get a number. But if you think back to our example in the text, right here, let's zoom back in, we don't actually get an answer here. Oh, is this the right one? I think I missed it. There it is. Sorry about that. We don't actually get the answer. We can guess the answer, but we don't actually get the answer. This is equivalent to our guess. This tells me, hey, somewhere in between them is an answer, and that's good enough. This is all you need to write for the answer on 24, and therefore 25 as well. Our work is these two values. Notice how they have to have different signs. If they were both positive, we would say, no, you can't use the IVT. If they were both negative, we would say, no, you can't use the IVT. So, according to the IVT, there exists c such that f of c equals 0. Let's reinforce the point. Let's look at 26. Going back to our homework. Okay. It says f of x equals x to the fifth minus 2x. And we have x equals 1 and x equals 2. So, how do we do this? Step 1. What's our a and what's our b? Our a in this case is 1. Our b in this case is 2. Okay? Step 2. Now that we've got our a and our b, we need to plug them in. So we need to take 1 and plug it in. We need to take 2 and plug it in and get an answer. 1 to the fifth is 1. 2 times 1 is 2. 1 minus 2 is negative 1. Okay. The bottom one. 2 to the fifth is 32. Minus 2 times 2 is 4. 32 minus 4 is 28. Notice how these have different signs. One of these is positive. One of them is negative. So what do we write as our answer? According to the IVT, there exists C, which is between 1 and 2, such that f of c equals 0. That's the answer. That doesn't feel good. I'm not going to lie to you. If you're used to the old ways of doing math, where you're talking like Algebra 1, Algebra 2, where you used to, get me the number, I want the number. We don't always need the number. Sometimes we just want to know where the number's at. Saying it's between 1 and 2 is really helpful, because 1 and 2 is a rather small range to be in. Compared to, it could be anything. It could be negative 50. It could be positive 27.5, It could be anything. But now we're specifically saying, hey, specifically between 1 and 2, there is an answer. And that's good enough. When you look at, if for example, you say you look at one of these homework problems. See if I can find a good one here. These have some nice ones. These have some nice ones. Well, a lot of these have nice ones. I was hoping there'd be a good picture down here. Lame. But if you have a picture where it's not necessarily a nice value, like, there are no good pictures. Dang. Here we go. Let's go right there. Look at this one. Like, you can't tell me what the answer is here, but you can tell me something close to it. Like, I could look at you and tell you, hey, it's between negative 1 and 0. Or it's close to negative 1, but between negative 1 and 0. Like, that gives me a good general idea about the graph. And if somebody's trying to read this, they can look at it and agree with me. Yeah, it's definitely there. Using the intermediate value theorem feels the same way. We don't get the answer, but we agree we know where it's at. Like, we know it's there. We don't really have to go any farther. We don't have to dig any deeper. It's between 1 and 2, It's between negative 4 and negative 2. Could it be negative 3? Yeah. Could it be negative, 2.1? Yeah. We don't know exactly where in between it is, but it's in between them. Could it be at 1.5? Yeah. Could it be at 1.1? Sure. Because that's also in between 1 and 2. We don't know exactly where it is. We just know it's here. And that's enough. So on numbers like 24 and 26, this is how you need to write your solution. And make sure you show your work. Show me that you do in fact get different signs. If you fail to show that we get different signs, you have not actually used the intermediate value theorem. You're just guessing. The whole point of the theorem is to know. So make sure you do know. Okay. So we've gotten our homework, we've gotten through the top section, just doing some factoring, got to the middle section using intermediate value theorem. Let's talk about the next big section, which is dealing specifically with how to find zeros and multiplicity. So let's talk about our next big term. Our next big term today is something called multiplicity. The idea of multiplicity is a solution appears more than once. Before I can talk about multiplicity, I have to tell you something that is a true fact. There's a term called a zero. A zero of a function is another name for the x-intercept. But it also includes its multiplicity. So a zero of a function is the x-intercept. If it's an x-intercept, it's also a zero. However, x-intercepts are not enough because sometimes you have something called multiplicity, meaning a solution that appears more than once. So a zero of a function will tell you not just that it's an x-intercept, but how many times it's a solution. And it's actually pretty easy to do. Let's take a look at number 30. I think it's easier to do these problems by just working on examples than trying to explain them. So on number 30, we have the following problem. We have f of x is equal to x plus 2 cubed times x minus 3 squared. Now, if we think back to how we found the x-intercepts, what did we do? Well, we used the fundamental theorem of algebra to break this into two problems. We would do x plus 2 cubed equals 0, and x minus 3 squared equals 0. Now, to get rid of the cube, we use a cube root. To get rid of the square, we use a square root, and we get x plus 2 equals 0, and then we get x equals negative 2. We do x minus 3 equals 0, taking a square root of both sides, doesn't do anything, and we get x equals 3 as our answer. So if we asked about the x-intercepts, our answer would be negative 2 and 3. But if it asks about the zeros, it's a slightly different answer. What you would do is you'd list both of these answers out. There's actually one more thing. The question is, how many times do they appear? And how we answer that question is based upon the number. If there is a power, then there is multiplicity. If there is a power, then there is a multiplicity. So since this first one, this negative 2, comes from a branch that has a power of 3, we would say negative 2 multiplicity 3. We would say the 3, since it comes from a branch with a power of 2, we'd say 3 multiplicity 2. So notice that this answer, negative 2, is found also in the x-intercept, but what is lacking is its multiplicity. It's negative 2, but it happens 3 times. And this actually makes a lot of sense if you remember how you can rewrite the first equation. A power of 3 just means you have x plus 2 times x plus 2 times x plus 2. A power of 3 just means you have that thing 3 times. A power of 2 just means you have that thing 2 times. If we were to do the fundamental theorem of algebra on this one, you'd have negative 2 appear 3 different times. You'd have 3 appear 2 different times. So when it asks about multiplicity, this is what it means. It means when you have a function that appears more than once. A term that appears more than once. Let's look now at 32 and see if we can keep this trend going. On 32, we have f of x is equal to x cubed times x minus 1 cubed times x plus 2. Okay. If we're trying to find the x-intercepts, we'd split this into 3 problems using the fundamental theorem of algebra. So let's do that. We would do x cubed equals 0. We would do x minus 1 cubed equals 0. We would do x plus 2 equals 0. And then we'd solve each one. The cube root of both sides would mean we get x equals 0. The cube root of both sides means we get x minus 1 equals 0, which means we have x equals 1 as an answer. And then when we subtract 2 from both sides, we would get x equals negative 2 as an answer. So these would be the intercepts. So if all it was asking about was the intercepts, that would be the answer. 0, 1, negative 2. But if it asks about the zeros, which is a different answer, we would have 0, but it appears 3 times. So 0 multiplicity 3. We'd have 1, but it also appears 3 times. This one, since there's no power on it, would mean that we have negative 2, and it's just multiplicity 1. When it comes to answering the question of what are the zeros, you have to list out the x-intercepts and how many times they appear. Because again, this top equation could just as easily be written as X to the third means x times x times x. X minus 1 to the third means x minus 1 times x minus 1 times x minus 1. And x plus 2 means x plus 2 is all that's there. So 0 is an answer 1, 2, 3 times. 1 is an answer 1, 2, 3 times. Negative 2 is an answer once. It's how we read the problem. And notice we get the same answers but have different meanings. 0 is an answer, but it's an answer 3 times. 1 is an answer, but it's an answer 3 times. Negative 2 is an answer, and it's only an answer once. This is multiplicity. Now, multiplicity, much like intercepts, is easiest done in factored form. But as you can see in some of our problems, some of them are not in factored form. You may have to factor them using various techniques. The AC method is great. Factoring completely by factoring out of each term is great. Using any of the shortcuts and factor by grouping, of course, is a good option. If you find you're having difficulty with any one of those, you may need to rewrite the problem. Because remember, this is what it means. It means how many times does that answer appear? 0 appears 3 times. How do I know that? X to the third tells me that, but so does x times x times x, because each one of these would be an answer. All right, the last part of your homework is being able to write an equation and then graph the equation. I think I'm going to pause right here and cover this piece on Monday. It means that we will cut our homework assignment slightly shorter. So instead of going all the way to, what was it? Our homework assignment was 7 through 63, every other odd. Instead of doing that, I'm going to make an adjustment to your homework assignment. Instead of doing 7 through 63, every other odd, I'm going to do 7 through 41 odds. We need the extra practice, so we're going to do that instead. So let's go ahead and go right there. That'll be your homework for tonight, section 5.3, page 390/408. We will discuss how to do the graphing portion of it next time. Be sure to take a look at these problems. Finally, tomorrow I'll be posting a video answering any questions that I have received throughout the week and addressing any of those questions. If you wish to have a question answered, please submit it to me before noon tomorrow, and I will answer that question in my video. Otherwise, that's going to be it for today. I hope you guys have a happy Friday, that you guys enjoy what's left of your weekend, and I will see you guys for sure on Monday.